So we're going to skip chapter 2's model 9 and 10 because those are non-linear models, and I have some momentum from the linear models that we've been considering up to model 8. So I'm just going to jump into chapter 3. We will leave the ending of chapter 2 for another time. So let's dive in. So chapter 3, I managed to find free versions of some textbooks that I actually used myself. They're good and they're free now. I mean, they're older editions, but the math is still correct, so it doesn't matter. So the links to them are there. I've taken portions of it from there. Sometimes I have blocked out places that are not germane to what we are talking about, but by and large, they are from these textbooks that I've referenced. So I'm not sure of the matrix algebra background of everyone in this class. So I'm going to assume that you know basically nothing. So we will skim through some of the simpler stuff. Of course, a matrix is an array of numbers. You know that. And a few things. We often denote a matrix by a capital letter. The entries in the matrix are a related lowercase letter. And the first subscript is the row it's in. The second subscript is the column it's in. All right. So you can see that notation there. A square matrix is a matrix that has an equal number of rows and columns. That's it. A vector is a matrix with one column. So you can see some examples here. And then the operation called a transposition or transpose takes the rows and columns of an existing matrix and makes rows into columns and columns into rows. And the notation we use is A prime. So the important thing to note is the dimension. If it's a 3 by 2 originally, then the transpose will be a 2 by 3. Two matrices are equal if they're of the same dimension, and so this is an and all the corresponding entries are the same. So we have a simple example in the book from the regression models that we've been talking about. Here's a simple one. And this notation is pretty standard. So the vector of responses, y1 to yn, so you can think of this as specifically like, let's say we're trying to predict someone's height using their weight. So the y1 to yn are the heights of n people. So these get stacked together in a vector. If you transpose y, you get y1 to yn like that, from left to right. The X matrix is called the design matrix. This stores all the predictor variable information. So if you're trying to predict the height of someone using their weight, then the heights will be the response, the y's. The weights of the n people will be the x1 to xn, like that. And of course, you can also find the transpose of the X matrix, and that would be just this. So these things are important in a little bit. So we'll see that. You add two matrices in a very intuitive way. It makes total sense. Subtract is the same. I'll note about the notation here. In a linear model, we basically are saying that the response is some constant mean function, or not. Okay, it can depend on the predictor variable, but it's considered non-random. So the notation yi equals EYI first. This means that the response can be said, all right, can be modeled as some mean plus some random element. Now the epsilon I is random. That's called the noise term. So if you look at the notation here, EYI, these are the individual means of all the heights of the n people. See? Stacking all of them together gives you the vector EY. So the definition of a vector of means is quite intuitive. So the mean of a vector is what you would think it would mean. It's just the expected values of each individual random variable stacked up like that. So you can write any statistical model actually, especially a linear model, as y equals to EY plus epsilon. So where does the X beta thing come in? So when we talk specifically about a linear model, we are giving a specific structure to what this EY vector looks like. In a linear model, we are saying that EY is the design matrix X times the vector beta, which contains all the parameters. All right. That is an assumption. So the linear model is a little bit more specific than a general statistical model that just says that, y is a function of its mean plus some noise. It's how the mean is specified that makes something a linear model. If you specify that the mean is the design matrix X multiplied by a vector of parameters, the betas, that makes this a linear model. All right, more on that later. How do you multiply matrices? I'm going to assume you have some background of that. If you multiply a matrix by a scalar, it's very, very straightforward. That scalar gets multiplied to everyone. If you multiply a matrix by a matrix, then first of all, it has to be conformable, i.e., let's say you're multiplying A and B, then the number of columns in A must equal the number of rows in B. And I think most of you know that, all right? So you can look at specific examples. This kind of detail is not really important to this class, so I'll just go over it. Right? You can see here an example of the X beta thing that I was talking about. If you look at additional example number 3, see, this is a very, very simple linear regression model. There's only one predictor variable. So you can think of X1, X2, and X3 as the 3 people's weights, right? And you see there's an intercept term, and then there's a slope term that gets multiplied to the weights, like that. This is the X beta structure that a linear model imposes on the mean, which I was talking about. One important transpose example is y prime y. If you take your response variables, y1 to yn, and then you transpose them and multiply them by itself, you end up with a scalar, and that scalar is the sum of the squares of the responses. This is an important thing. The matrix X prime X is also important. You can see how that's computed. The matrix X prime Y is also important, but somewhere in the future. So just these are important specific examples that you can look at. All right. So we've talked about these things. Let me just define what a symmetric matrix is. A symmetric matrix, first of all, is any square matrix whose transpose is the same as itself. All right. So if A and A prime are the same and A is square, then we say A is symmetric. All right. So you can see some examples here. So at this point, I will ask you to work on group work 14. And I want you to look specifically at questions 6 through 10 first. 6 through 10. Some of these are repetition. We denote the transpose of a matrix A by A prime. We know that. So I want you to answer 7 and then look at 8. This is something that I will cover in a few minutes, but you need this now to prove 9, right? It can be shown that if A and B are conformable, so you can multiply them, the transpose of the product of A and B is the product of B transpose A transpose. So look at the order. AB entirely multiplied, then transposed, is B transpose A transpose. Again, you might know this already, but I'm stating it here for completeness. Now, you're going to need to use this to prove number 9, right? So work on 7. 7 is just a definition. 9 is what I want you to show, and it's a 1 or 2 line proof, so don't overthink it. It's pretty basic. So try to prove number 9. Let's continue now with our slides. A few important special matrices. One is the identity matrix. So the identity matrix has the analogous role of the number 1 in real numbers. The number 1, you know, if you pre-multiply or post-multiply with any other number, doesn't change that number. So the identity matrix is the matrix matrix analog to that. So if you take the identity matrix and pre-multiply it or post-multiply it, it doesn't do anything. So AI is IA is A. Now, one thing I'll say is the identity matrix, its form is, it's first of all, it's a diagonal matrix. So a diagonal matrix is a matrix where only the diagonals are non-zero. They could be zero as well, but every off-diagonal entry is zero. So it's a square matrix whose off-diagonal entries are zero. That's a diagonal matrix. So an identity matrix is a specific diagonal matrix whose diagonals are all one. All right. A few other terms just to mention. The boldface vector 1, like that, is a vector of ones. This is just shorthand. The boldface J matrix is basically a matrix whose elements are all one. Okay, you can see some examples here. And I think you can work out why 1 prime 1 produces the scalar n, but 1 1 prime produces the matrix J. All right, so you can work that out. The 0 vector is a vector of zeros, but it's bold. All right. We now come to the concept of linear independence or dependence and the rank. So take a careful look at this matrix A here. You can see that this matrix has 4 columns, which can be thought of as 4 vectors. So the vector 1, 2, 3, 2, 2, 4, 5, 10, 15, and 1, 6, 1. So I want you to think carefully. If you look at the choice of these vectors, do you notice that 5, 10, and 15, this vector, vector number 3, 5, 10, 15, you can actually get it by multiplying 1, 2, 3 with the scalar 5. If you take 5 times of the vector 1, 2, 3, you do produce 5, 10, 15. Now, this just means that 5, 10, 15 is linearly dependent on 1, 2, 3, and vice versa, which means there can be no more than 3 linearly independent vectors in this matrix. So the definition of linear independence is something I believe you should know if you have taken any linear algebra course in this school, but I will revise it now. This book uses linear dependence definition, but I think it's easier to understand it from linear independence. If you set a linear combination of the vectors C1 to CC by multiplying each vector by a scalar, and you set this to 0, right, the 0 vector, we say that the vectors C1 to CC are linearly independent if the only way this can happen is all these scalars have to be 0. Otherwise, if you can find not all 0k's such that this can equal 0, then they are linearly dependent. So for example, if you look at an alternative, this is just a slide. If you look at this thing, you can see that 5 times this vector minus this other vector produces the 0 vector, which tells you that these set of vectors are not linearly independent. So then, what is the rank of a matrix? The rank of a matrix is the maximum number of linearly independent vectors that you can generate, I guess, from those columns. All right. So you can show this. I don't require it today. You can show that the rank of the matrix A here is 3. It's not 4 because we've already shown that 5, 10, 15, and 1, 2, 3 are linearly dependent. So the highest rank it could be is 3. It might be 2 or even 1, right? Without checking, but it can be at most 3. So here's another rule. The proof is not difficult, but it's not required in this class. The rank of a matrix and the rank of the transpose of that matrix are the same. This is not, unless you have supernatural linear algebra prowess, it's not something that's immediately obvious. All right. The rank of a matrix and the rank of the transpose of the matrix are the same. All right. So the largest rank this could have is 3. All right. Now it turns out it is 3, but that's besides the point. All right. Why is rank important? Rank is important because we are going to enter the concept of an inverse. Now, a square matrix is invertible. A square matrix is called invertible, or the inverse exists if the matrix itself is full rank. Now, what do I mean by full rank? It means that if you are an n by n square matrix, then your rank is n, right? right? A matrix is full rank, a square matrix is full rank if its rank equals its number of rows and columns, right? That kind of matrix will have an inverse. Okay, so talking about the issue of rank, just to see that whether you understand this concept, I want you now to work on example problem 10 in group work 14. For matrix A equals that thing, give examples of A so that rank A can be 3 or 2 and also 1. See whether you understand the concept of rank, okay? So work on problem 10 now, and then come back and we'll talk more about inverses. All right, so the inverse of a matrix exists for square matrices that are full rank. Now, I'm not actually so interested in this class of asking you to find inverse matrices. They take too long unless they are very special diagonals, diagonal matrices. It takes quite some time. But I think you should not uh, be a math grad and not know how to find a 2 by 2 inverse. So you can check the formula for this. It's pretty basic. I think most of you know this. All right. I will not require you to do this 3 by 3 inverses in class for exams and stuff like that. It's quite tedious. We'll always use software to get those. All right. An important thing that I want you to look at is the x prime x matrix inverse. Right. Right. Again, this is a famous one that we will be using in future. All right, the x prime x inverse matrix, but more about that later. I now want you to think about the remaining questions on group work 14, problems 1 through 5. Right? Humor me, do 1 and 2 just to show that you know how to multiply matrices. Okay. Answer 3. Now, one thing I want to point out is when you have a matrix inverse, if a matrix has an inverse, all right, the role of the inverse is when you pre-multiply or post-multiply the original matrix, you will produce the identity. And I think you know that. All right. What I want you to show in this proof is that if a matrix if a matrix has an inverse, if the inverse exists, it is unique. So see if you can work out problem 5. Again, this is a 1 or 2 line proof, so don't sweat it if you find it really, really difficult. It's, again, just thinking very carefully about what operations you can do on a matrix. Try, challenge yourself, see if you can prove that if a matrix has an inverse, it has to be unique. Okay, we'll continue now with our talk on matrices. Here's a page of very, very important results that you should know. Addition is commutative. You can do one or the other first. It is associative. You can do A plus B first or B plus C first. And even the order is commutative, so you can change. AB first, then C is the same as A, then BC. But the order is important, right? I think you know this. Matrices A times B is not necessarily B times A. There seems to be some kind of analog to factoring a matrix. This makes sense. If you multiply a scalar to a sum of 2 matrices, that scalar has to go to both. The transpose of a transpose is itself. The transpose of A plus B is the transpose of A plus the transpose of B. All this can be proven, but the proofs can be quite tedious, so we won't require them. This one I've already mentioned, very, very important, 5.32. AB transpose is B transpose A transpose. More generally, ABC transpose is C transpose B transpose A transpose. Here's an important one. AB product inverse is B inverse A inverse. ABC inverse is C inverse B inverse A inverse. The inverse of an inverse is itself. And here's an important one that's not very well known. I don't know why. The transpose, the inverse of a transpose is the transpose of the inverse. It's a very, very useful property that will get us out of a lot of jams later, all right? We will conclude now by looking at what's a random vector. I've already talked about this. A random vector is a vector of random variables. So it's not a constant vector. A constant vector is a vector with constants. But y1, y2, y3 can be random variables. It could be heights of people, 3 people in this case. So this is called a random vector. The expected value of a random vector is very intuitive. It just means take each random variable and find its expected value and then pile them up like that. So the expected value of a vector is easily defined. So you can see that here's an example. The noise term, 3 noise terms, it is a model assumption. This is not something you can prove. It is a model assumption that the expected value of all the noise terms is 0. So E epsilon is the 0 vector. What is probably new to this class, and we will end on this particular page. I'll be giving one last group work, but we'll talk about this. What is the variance covariance matrix? Now, this textbook uses a bold sigma square y like this. I don't like this notation. I just call it VAR of the vector y. One thing to note is the variance covariance matrix of a random vector is exactly that. It's a matrix. So the variance of a vector is not, it's not piling up the variance of y1, the variance of y2, the variance of y3. That is not correct. The variance of a vector is not var y1, var y2, var y3. That is not correct. The variance of a vector is actually a matrix that shows all the covariance structures of the random variables. So you can see that this term in the diagonal, this is the variance of y1, this is the variance of y2, and this is the variance of y3. That's quite straightforward. But what are these? So from 365 here, these are the covariance terms. So the off diagonals give you the covariances between the random variables. So like y1 and y2, what's their covariance? y1 and y3, and you can see y1, y3, this is the 1, 3 position, this is the 1, 2 position, this is the 2, 3 position, like that. So these off diagonals give you the covariance structure, while the diagonal terms give you the variance structure of all your random variables. So this is very, very important to note, and this is new. All right. This is not as intuitive as the expected value of a random vector. That one's pretty obvious. You just take the expected values. But covariance matrix, it highlights the variances in the diagonal, yes, but it's covariances in the off diagonals. One important thing to note is it is an assumption in a linear model that all the responses, y1 to yn, are all independent. So what does that mean? If you know from Math 365, if random variables are independent, then the covariances between them are equal to exactly 0. In other words, a linear model has a very simple variance covariance matrix. It assumes only these terms could possibly be non-zero. Every off diagonal is 0 because the model assumption in a linear model is that there are no covariances, right? Actually, there's an even stronger assumption of independence. So with that, this part is not so important. This is what I was talking about. A linear model has a variance covariance matrix that looks like this, all right? It assumes, right, that the noise terms are not correlated. Each noise term has a variability, and that variability is the same. So you can see the sigma square, sigma square, sigma square, like that. This, of course, you can factorize out the sigma square if you want. So very often, people write this as sigma square times I, right? The variance covariance matrix of the noise terms in the linear model is sigma square times the identity matrix, like this. Okay, so at this point, please work on group work 15, and that is actually all for today.